Yeah, hi folks, this is the next video for the further maths year 1 pure. We're still on with vectors. What we're looking towards 9b. So we've talked about the vector equation of a line. Now I want to talk about the vector equation of a plane. So a plane, think about just a flat piece of paper. With a line, remember, the vector equation of a line, we needed a position and a direction part. Well, a plane, and I'll draw it as best I can, there's my 3D plane. What I need is a position and two directions. And that defines any plane. Now, I'm looking at the formula booklet, and we're actually told all this, but we need to understand it. So the plane with position vector. Okay, let's write it out. The vector equation of a plane. The position on the plane, any position on the plane can be got by the position vector plus lambda and mu multiples of the two direction vectors. So A is a position vector, a point on the plane. Oh, there goes my pen. Down to blue. Position vector. B is a direction vector. And C is another direction vector. Now, of course, if B and C were parallel, that's no good at all. So B and C are not parallel. Otherwise, I can only go in one dimension on my plane. So the position on the plane, if you like, locates how high up it is. The directions describe which way it's tilting. I hope that makes some sense. So if I have 3 points on the plane, well, I can find two direction vectors and I can use one of the points for my position vector. And that's what example 7's asking us to do. It gives me 3 sets of coordinates. 3, 2, minus 1, and 4, 3, 5. Just at the end of my book, pages aren't very flat. And I want the plane. So I'm going to go from, I can do any combination. My direction vectors are going to be, I'm choosing to do A to B and A to C. So the direction vectors, I'm going to do AB. Well, how do I get from 2 to 3? I add on 1. How do I get from 2 to 2? I don't go anywhere. And how do I get from minus 1 to minus 1? I don't go anywhere. And I'm also choosing to do A to C. 2 to 4, that's 2. 2 to 3, add on 1. And minus 1 to 5, that's 6. Now just a quick glance, none of these will simplify. These aren't multiples of, if that was a 2 I could halve everything, but I shan't bother. I can use any of these as my position vector. So an equation, I'm going to use the position vector of A. So 2, 2 minus 1 plus lambda 1, 0, 0 plus mu 2, 1, 6. Coincidentally, and I hadn't looked at this before, they've actually done that. They've used those points in the book. But of course, my direction parts could have been A to B, B to A, B to C, C to B. There's a load of different possibilities I could have had for my direction parts, and 3 different possibilities I could have had for my position parts. So there's a lot of different possibilities that I could have used to describe the same plane. I just need to get a new book, hold on. I was an idiot, folks, and I made a mistake, so I'm just going to talk you through example 8. I've written it out, verify that the point lies in the plane. What I've done is I've set the position vector equal to the equation of the plane. That generates me 3 equations. Now I've written those 3 equations in the format that the calculator likes them to solve simultaneously. And I've got 2 unknowns and I have 3 equations. So what I'm going to do is I'm going to solve using the first 2 equations. I'm going to find the value of the unknowns. And I did that, look, use equations 1 and 2 to solve. So I got my values of lambda and mu. I used my calculator to solve simultaneously. And then verified that they worked for equation number 3. Sub in mu and lambda. Sum of my values of mu and lambda for equation number 3. And I get minus 1 plus 2 equals 1, which is correct. Therefore, P lies on the plane. If P didn't lie on the plane, then I would not get consistent values for mu and lambda. So the fact that the same values for mu and lambda work for all 3 equations means this point must lie on the plane. Okay, example 9, we'll just need to do a bit of talking through first. Now, we don't need to prove this. We are told it in the formula booklet. If I have my plane, another way of writing the equation of the plane, or if you like, rather than the vector equation, I can write the Cartesian equation. Remember, that's the one that connects x and y and z. I could write Cartesian equation of the plane. I could write some value ax plus by plus cz is a constant. A, B, C and D are constants. You just got to believe me now, because we are not in a position to prove it. We are going to prove it later on. This vector that's perpendicular, the perpendicular is called the normal vector. This vector A is ABC. So given the Cartesian equation of the plane, remember this is where we talk about the relationship between the values of x, y and z on any point on the plane. This form of the equation means I can write a vector which is perpendicular to the plane. And that's a different way of describing the plane given its perpendicular vector. In the formula booklet, let me find my mouse, here you go. In the formula booklet, I write out what we're given. It says the plane through A, the plane through point A with normal vector n equals n1, n2, n3 has Cartesian equation n1x plus n2y plus n3z equals, oh no, they actually put it like this. They make it equal to 0. They put all the constants on one side. Now, I'm not going to bother with describing this d yet, because we haven't quite done that math that we need to do. But just another way of describing the plane. I can get my Cartesian equation and come up with the normal vector. Example 9 says the plane pi, capital Pi, the plane pi is perpendicular to the normal vector 3, minus 2, 1, and passes through point P, which is 8, 4, minus 7. Find a Cartesian equation of the plane. Find this. Well, I've got ABC, 3, minus 2, 1. I've actually got values of x, y and z. So I should be able to find D. Well, I can find D. I'm just going to sub in. So I know that the plane looks like this. 3x minus 2y plus z equals D. I've got x, y and z being 8, 4, minus 7. So I just sub in 3 lots of 8 minus 2 lots of 4 minus 7 equals D. So D must be 9. So the plane pi, capital Pi, 3x minus 2y plus z equals 9. Now we're going to do a lot more work on planes, but for the time being, this will do us. 9b. Good luck.